Don't get this MCAT question wrong.
In the Hnmr spectrum for the molecule shown below, what is the signal ratio area for proton environments for metal carbons? So basically, Hnmr in general, they'll show all the peaks for all the different hydrogens, but this is specifically asking for metal carbons. So we have to identify our metal carbons, right? And so we have one over here, and it has these three hydrogens. We have one up here, which has these three hydrogens, and then we have these on the bottom, right? We have these three, and then this one. And so the idea is that, let's say this is your Hnmr graph, right, spectra. Your metals in general, or alkyls, will just be between 2 and 4, so I'm going to draw those in. And I'm going to give you all like a separate molecule right here. What it's trying to show is like, this is 1, 2, 3 carbons, right? So we have 2 hydrogens up here, and then we have 1, 2, 3, 1, 2, 3, right, hydrogens. Basically, your peaks, right, the sizes are going to depend on how many hydrogens are there of that specific peak, right? So when I say between 2 and 4 for metals or alkyls in general, that means like, you'll have stuff in between, but depending on the metal or the alkyl group, it could be a little bit left, a little bit right, right? Like this carbon is a alkyl, this carbon is also alkyl. They'll be between 2 and 4, but they'll be in different spots just based on their features. And so let's look at this carbon right here. We have 1, 2, and 3 hydrogens, right? But this one also has these 3 hydrogens because these 2 carbons are the same. This has a plane of symmetry, and so these carbons are the same. So actually, instead of 3 hydrogens, we're going to have 6 hydrogens on the peak. So I'm going to draw this right here, okay? I'm going to put a 6 up here. This is like your peak. And there's splitting and stuff, but we're not going to get into that because it's irrelevant to this. Now, this carbon right here, it has 2 hydrogens. And there's no other carbons. This is a 3-carbon molecule. And so this one has 2, right? And that means that this related peak is going to be a third of this, right? We're going to draw it like maybe like this. It's going to have 2, okay? And so as you can see, this corresponds to this molecule, this tall peak with the 6 on it, is referring to the fact that we have 2 same carbons, right? These 2 are not unique, they're both the same, and in total we have 6 hydrogens, whereas this one is its own unique carbon with just 2 hydrogens, and so that's why it looks like that. So we're trying to use the same logic over here, determine how many unique carbons there are and how many overall hydrogens are, corresponding to each like unique carbon, okay? So let's look at this first one right here. This one has 3 hydrogens, obviously. Now this carbon, are any of these other carbons the same as this one? The answer is no, because this carbon is bonded directly to this 5-member ring, while this one's bonded to a 6-member ring. This is not even directly bonded to a ring, and so this is its own thing. So right now we have 3 hydrogens, right? 3 hydrogens. Now this is like a ratio. Let's check out this one right here. Obviously we determined that this is different from this one. This is directly bonded to a 6-member ring, while these 2 are not. So this is its own thing, has 3 hydrogens, so we have another 3 hydrogens. Now let's look at this one right here. These 2 are different, okay? We determined that. Now this carbon has 3 hydrogens, but this carbon has 3 hydrogens, obviously, but these 2 carbons are the same, right? They're both metals attached to this CH, which is bonded to this, and this CH3 is bonded to this CH, which is bonded to all that. So these 2 are the same. There's like a plane of symmetry right here, meaning that these 2 are the same. So now we have 6 right here. So in total, there's 4 metals, but there's 3 unique metals. So we have 3 to 3 to 6, and that matches answer choice C.